Okay. Um, Hello to the class. Um, we will continue with. Oh my goodness. Okay, sorry. We'll continue with. And my slides were on the other computer. So hold on a second. Sorry about that. I just switched laptops. Um, and okay. Let me not panic. And hopefully uh, hmm. Okay, and no, it's not the most recent version, but it's too late. Okay. Sorry about that. Okay, so it doesn't matter. There were some cosmetic changes, but everything is we can use on the previous version of the slides. So it's not it's not going to be a dramatic impact um, if we use this version of the slides. Okay, no. Okay, finally. All right. Um, so we'll talk about strong induction, but we'll first actually do one more inductive proof uh, just for the sake of good old times when all we had was induction. So um, here is something that we can prove by induction. I left it off from the last lecture. So um, recurrence relations. Okay, hold on. And I'm getting a phone call on this laptop, which I don't know how to switch off. These type of calls. I don't know how to switch them off because I have to be obviously connected. Yes, but maybe if I just sign off from Google completely, then I could. Okay. Um, okay, back we are at the slide. So here is a very typical thing you can prove by induction. You have a recurrence relation defined. Here is an example. H0, the base case, is -2. And here is a recurrence relation. Hn is 5 times the previous sequence element plus a fixed term, an. Okay, it's not fixed, it's linear, but the point is it does not depend on previous values of h. So I hope everybody can hear me fine. Okay, so now there is a recurrence relation. You can compute it for the first few elements. And perhaps you will have a guess about what this recurrence relation, that it actually has a closed formula, concise closed formula, and it's this one. Why this one? We'll actually see this in a few weeks. But perhaps you can simplify this and see, okay, what would happen if hn was 5 hn minus 1 without this term? Then this is actually a geometric formula, right? So you would have just powers of 5 accumulated. These powers of 5 are here, but they're offset. First of all, by this proportionality constant, which is not apparent in this relation. Where did this 1/2 came from? And a linear and a constant term. That there is some linear term you can expect perhaps, and then there's some constant offset. Well, yes, but where did the 1/2 came from exactly? So you will see. Let's now see that induction can. How would you use induction to prove that this is a closed formula? So what are you proving? You're proving a predicate that says that for any n, you're proving the following predicate about n. Okay, the predicate is the nth element of this recursively defined sequence, namely the recurrence relation, sequence defined by a recurrence relation, that this nth element of such an object has the following closed formula. You can think of the right-hand side as some function of n, call it f of n, and what we are proving is that this recurrence relation defines a sequence such that nth term of it is equal to f of n. Okay, so in the base case, what are we checking? That this sequence at index 0, the value of it has the property that it is equal to f of 0, where f is this function. Okay, so let's evaluate this function at 0. Okay, we do. So 1/2 to 5 to the 0, so this is a 1, minus 2 to the 0, so this will drop out, right? N is 0. Minus 2.5. Okay, so this is 1. So it's 1/2 minus 2. This drops out, minus 2.5, minus 2. Great. What I've done here is that I checked that the H0 defined in this recurrence relation in the sequence, which is the base case, so like actually in that case, you don't even look at the recurrence relation, but still, it's a sequence defined by this base case and recurrence relation. That for the index 0, it does equal to this function evaluated at 0. Okay, what do you need to prove in the inductive case? Here is the recurrence relation again, and here's the theorem that its values are equal to this function of n. Okay, so in the inductive step, you have to prove that for every k starting from 0, if this predicate holds about index k, which is this statement, then the same predicate will hold at index k plus 1, which is this statement, right? This green and red thing, it's p of k. This is the predicate at k, and this is the predicate at k plus 1. And similarly as in examples on Wednesday, is the relation between left-hand side of these equations that will let you prove this thing from this thing. And what's the relation? It is given by the recurrence relation. These are recursively defined objects. So its definition at index k plus 1 is actually stated in terms of whatever this object was at index k. So let's use it, right? This is by recurrence relation, I can rewrite the purple guy as the 5 times the green plus this term. Now, don't mess up values. So this is where it's kind of better to do this for a different variable, k, because now you read off, okay, that k plus 1 is, okay, so it relates to k. You can instantiate this. What are you instantiating this with? What is n? N is k plus 1. So therefore, n minus 1 is k. And therefore, n is k plus 1. If you try to use the same variable n, you can. It's just that you can mess up that step. If you use a separate variable, it's much easier to keep yourself honest and not make a mistake. Okay, at this step. Okay, so you have rewritten this good, and now we are in good shape because by the inductive assumption we can assume this equality holds. That was the predicate at k, which we can assume in order to show that the predicate holds at k plus 1, right? So let's do this rewrite. This is by the inductive hypothesis, by this assumption. So we are rewriting hk as this thing, and not forgetting the rest of the arithmetic formula. So the fact that this is all multiplied by 5, and that 8 times k plus 1 is added. Okay, so the rest is arithmetics. You're hoping that you are hoping, I'm sorry, this again, so okay, you're hoping that this arithmetic stuff is equal to this. Okay, so the rest is arithmetics in order to show that this line, it really is that one. However you arrive there, you know, good luck to you, right? You can see how we do it. It's so it's 1/2 times 5 to the k, so this is going to be 5k plus 1 as you need it. Okay, now don't forget that this 5 has to be, this stuff has to be multiplied by 5. Okay, and this you cross multiply, done, right? So this is in a good form, and now we're just grouping elements. So minus 10k plus 8k came here, minus 5 times 2, okay, 5 times and a half, so that's minus 12 and a half, 8k here, okay, and 8, so it's minus 4 and a half. So, but why? Okay, because I need here to be minus k plus 1, minus 2 k plus 1, right? So I'm going to put 2 here. This 2, I'm going to kick it out, right? Put it over here. So that's where it is. Okay. This is just arithmetics. Okay, so stare at it, and it should be true. And there is like, this is not set in stone. Like you can do it. Any sequence of arithmetic operations that shows this line, this one, is equal to this blue expression, you can do it in a million ways, right? It doesn't matter how you do it as long as you do it, right? I mean, you don't cheat doing it, right? Like you don't force this expression to be that one, even though that's not the case. Or like pretend that you made some steps that, you know, it's inequality, but like it's not clear what has happened. All right. All right. Let's try to do this for, so we have a what did we do? We had a recurrence relation, started somewhere, was defined recursively afterwards, and we had a closed formula for it. And induction worked to prove that this closed formula is always correct about any element in this recursively defined sequence. So let's try to apply it for Fibonacci. Fibonacci sequence, you have the starting points, 2 of them, and then after this threshold, the next guy is defined in terms of the sum of the previous 2. Okay, so Fibonacci sequence grows almost like a geometric series. If instead of summing the previous 2, you just sum twice this guy, then it would be a geometric sequence. The next guy is twice the previous. So, so if you evaluate this, you will see that actually it does grow. You know, a geometric sequence of base 2 is an upper bound for every Fibonacci term. Okay, so let's try to do it with an induction. Prove this claim that it always holds for all the elements in this recursively defined sequence. So it is true about the first one. Okay, now first attempt at an inductive step. Show that if the bound held at the previous one, then it's going to hold at the next. So this is the P, predicate P here, instantiated with the K. Here's the same predicate instantiated with the K plus 1. Now we can't prove this because at k plus first index, the value of this sequence is defined as the sum of kth and k minus first element. But so, for example, for k equals 0, this would, we want to argue that if f0 is bounded, then so is f1. But f1, we would somehow need to reference the k minus first term, which would be minus first, right? So, okay, so this is undefined. Okay, so let's try to, so maybe we should just shift the base case, right? Don't start with a 0, do 1 as part of the base case, and then use the induction for the rest. Okay, so yes, the base case works. F of 0 is 1, and it is upper bounded by 2 to the 0, which is also 1, and this is not a strict, right, inequality. Of course, 2 to the 1 is 2, and this f1 is actually 1, so here's strict upper bound. Okay, so far so good. Now, so how about use induction to argue that it holds for all greater than 2, right? So at k equal 1, whenever I have k at least 1, I can argue that that this bound holds, assuming this one does. But I can't. So that was on my fixed slides, but whatever. I can't argue this because if you try to argue this, then f of k plus 1, well, you can rewrite it as fk plus fk minus 1. Okay, so far so good. And you can use this bound on fk. Good, but then there will be a fk minus 1 term that you cannot upper bound by anything, because what you are assuming here is just that the bound holds for the previous one. That's what induction is. You're assuming something is true about the previous element. Then you're hoping that suffices to prove that it's true about the next. It won't suffice in this case, because fk plus 1 is fk plus fk minus 1. Fk is upper bounded by 2 to the k, but what about this fk minus 1 guy? You don't know how to upper bound him. You don't know, why can you assume that he is also upper bounded by something? Like, let's say the same 2 to the k, then the 2 added would give you this. So that's where strong induction comes in. We could prove this theorem that all terms of Fibonacci sequence are upper bounded by this geometric sequence 2 to the n. It's this exponential function, right? If we were allowed to modify how the inductive step looks, the base case would still be the same as on the previous slide. You just check by hand that this is true and this is true, which it is, because f0 is 1 and f1 is 1, right? But you modify the inductive step so that instead of trying to argue that the predicate is true at step k plus 1, based only on the assumption that the predicate is true about an index immediately before the one you're trying to prove about, instead you add yourself more facts that you can use in order to argue this one. And you give yourself that the predicate is not only true about the number, an immediate predecessor, it's also true about the one before and the one before, and in fact all of them starting from the base case. Now, if you could use such a, if proving this implication also implied that the predicate is true, then you would be home, because okay, I guess I should at this point switch to the document camera. And hold on. Okay. So I have that f0 is greater or equal to the 0, and that f1 is greater or equal to the 1. And I have that fn is fn minus 1 plus fn minus 2. And the theorem is that for all n greater or equal to 0, fn is upper bounded by 2 to the n. Okay, so that's my predicate, p of n. Okay. Hold on a second. Let me remove okay. So the base case we have seen. So the inductive step. Let me copy what I am doing here, right? So I'm proving that for any k equal to 1, so the choice of these indexes is really arbitrary, right? Like you can shift indices. So I'm choosing this one. It's not set in stone. If f0 is upper bounded by 2 to the 0 and f1 is upper bounded by 2 to the 1 and dot dot dot, and in particular fk minus 1 is upper bounded by 2k minus 1 and fk upper bounded by 2 to the k, if all of that holds, then the predicate holds about the next one. So fk plus 1 is upper bounded by 2k plus 1, right? So this is p of k plus 1, pk, pk minus 1, p2, p1, p0, right? Okay. So how do you prove that? So fk plus 1 is, and now we can use the same technique as before, as in the case of the first recursive defined sequence, right? The proof I did first in this lecture. So fk plus 1 by this formula, n is k plus 1, so this is fk. Okay, and it is, it's just the sum of sum of the previous two terms. And now by this inductive hypothesis, I can upper bound this guy by 2 to the k, and I can upper bound this guy by 2 to the k minus 1. And that's great because that's definitely smaller than 2 to the k plus 2 to the k, right? Which is equal 2 to the k plus 1, right? So this is smaller than that. Okay, and I'm done. So right at this time, so here is by recurrence relation, this one, and here by strong inductive hypotheses. Technically, I actually didn't use all of this stuff necessarily. I used the fact that pk minus 1 was true and the fact that pk was true. Okay, that's I could have used all of them if I needed, but because it's a conjunction, so in particular these are true, and so I'm free to use these, right? And that's the ones I used. If the index, for k equal 1, these two would be these two, right? Which also tells you that you cannot do this for k equal 0, because now you would be here and you would be using some f minus 1, which does not exist. You can shift the indexes here. You can, if you can you can call this k minus 1 and call this k, but you just have to be careful and modify the bounds, the ranges appropriately to reflect that. Okay, let's go back to the to my slides. Okay, that didn't do it, right? You still have my piece of paper, right? Not my slides.
We see your slides.
Oh, you see my slides now? Okay. Okay, good. So okay, so here is the strong induction as a, in the general terms. You're proving some statement parameterized by integer as before, some predicate, and there is some threshold t. In the case of Fibonacci, it was t equal 1 or 2 or whatever. Okay. If you know that the predicate holds about a few consecutive integers in here from 1 to t, then you can, and that's your modified base case. For the case of a simple induction, this was just one statement here, that the predicate is true about 1 point. In a strong induction, it's a range of points. And then if you prove the following statement, for every k starting from here, that conjunction of these statements implies that the predicate holds about 1 more. Then if these two statements hold, then that suffices to prove that the p is true about every integer starting from this one. Now just note, I can write this implication a little faster. For all k greater or equal to this threshold, for all indices in the range, if predicate holds on them, then it holds about 1 more than the end of the range. And the starting point is sort of arbitrary. Like I gave you here an example where you want to prove a predicate for all n greater or equal to 1. In fact, just on the previous slide for Fibonacci, we argued that the bound holds for n equal to greater or equal to 0. What would change in this picture if the starting point was 0? Here, I would have to have p of 0 as in my list of base cases. I would be allowed to use p of 0 in this part, in this implication. And this part would also, right, because it's the same. So I don't want to make too many variables on this one slide, but because then it's impossible to understand that thing. But be aware that also the starting point might change, right? And it just did change. On Fibonacci, it was 0. Who says that strong induction, is a good principle? Why should it be suffice to prove these two things in order to prove that the statement is true for all n? Well, it's the same domino effect. So if you have this conjunction is true, then therefore the predicate is true about all indexes from 1 to t. So let's look at, is it true for t plus 1? Well, let's instantiate this implication for k equal t. You prove this implication in general for any k greater or equal to t. So in particular, it works for t. So what does this instantiate to? Exactly the base cases. And therefore, because they are true, the implication will also imply that p of t plus 1 was true. So now you can add your the fact that the predicate holds at t plus 1. Essentially, you can add it to your, the statements that are already known about the world. So you can add them to the base cases, if you will, and then just recurse, because the same procedure will imply that p true is for t plus 2. you add that and you recurse, right? So because you can do it for any integer n, if n is a million, this proof will take a million steps, but it exists, right? And all, so it can be enveloped into these million step proofs, right? But it exists, and therefore it's true. Although the principle of induction in mathematics, in formal mathematics, is kind of a thing. Like, what does it mean that you have a proof that is, it exists, but not exactly explicitly. So, so in mathematics, there's sort of formal methods for what we can prove and what we cannot prove, and what kind of assumptions we need, or proof methods, and are they all equivalent? And there is sort of two views of this whether you allow induction as a method sort of cuts mathematics into divides mathematics between stuff that can be proven without induction and stuff that we only know how to prove with induction. But that's philosophical for us. So we'll just not go there. All right. Okay. So let's look how this relates to these initial conditions. So let's say that you're proving a predicate P about all integers starting at 0.4. And let's say that your base cases were 4, 5, 6, 7. So these somehow you proved by hand that they all work. What I should not say must, needs, I guess, because you can have different forms of strong induction, but what the kind of things that it would suffice to prove in the inductive step? Yes. So I have Hagen with a D. Anymore? Okay. Rishabh, yes. Matt, you good. So you have, this is the right one, right? Because this is a sufficient one. This is the most relaxed one indeed. If you proved this, it would also work great. If this was true, then this would be implied. But what I'm saying here is that this suffices. It's actually it's more relaxed form. Like, this implication might not be true, but while this one is, because this implication basically adds more to the left-hand side of right, to what you assume in the application. So you know that some fact by itself might not imply something, but if you add something to that fact, then the two will imply something you want. Okay. So and now, which statement now recognize the statement for which is this the inductive step in the strong inductive proof, that for all k at least 7, conjunction of all these implies pk plus 1. Okay, I have a few A's. Okay, and I have a first B. No, so what's wrong with A? pk is true for every k between 4 and k. This is self-referential, right? You cannot, this is a universal quantifier. The free variable is k. And then you define the range of this variable, the domain of this variable as an interval between 4 and k. This you cannot do, right? You cannot define a free variable in terms of a range who you denote with the same variable. So it is B. Every index in this range, if the predicate is true about every index in this range, then this is correct. The problem with this one, just answering the chat stuff, is again, you cannot write a formula like for every k in the range from 4 to k, because it's self-referential. Like I'm defining A as 2A. Okay, I can only define A in terms of some expressions that does not involve A. I mean, like this stuff involves the same predicate, right? Or a recurrence relation involves sort of the same sequence, but no, these are actually different elements, right? Like the nth is defined in terms of n plus n minus first. Okay. So here is another example of something you can prove by a strong induction, and it's like it's not clear how to prove it by induction. Although actually, everything that you can prove by strong induction can be cast as an inductive proof of a sort of modified predicate. Namely, the predicate is that it's like a higher level predicate. Think of P prime, a predicate P prime that says that predicate P, so P prime at K says that P holds for all indexes between 1 and K. It's a kind of higher level predicate. It says that this P prime statement at index K is true even only if P is true about all range from 1 to K. Then you can think of this implication as an implication showing that P prime at K implies P prime at K plus 1. And why is this is not apparent? Where is the conjunction with all the rest of this stuff? But it is equivalent because it's sort of like the fact that you all assume this. So implication A implies B is equivalent to an implication that A implies B and A. So I could copy all of this and stick it in here as one big conjunction with this guy, because that would be A implies B and A. It's equivalent, like adding the hypothesis of induction in the target, it's an equivalent thing. So therefore, it's this guy's induction, really. If you think of this higher level predicate that says everything is true on the range between 1 and the index. So in that sense, strong induction is really the same as induction, okay? But all right, still in the practice of doing it, you will see a difference, right? Okay, so suppose you can, here's an example of the kind of stuff that you can prove with strong induction. My statement is that any value of n cents can be expressed as a bunch of 3 cents and 7 cents stamps. So it would suffice if the post office has only 3 cent stamps and 7 cent stamps. They can are free now to create mail categories at so that like it's 27 cents or $1.15. They don't have to think, like everything is expressible by a bunch of these 2 stamps. So let's see. But that is true only after a certain threshold. Okay, and it just happens to be 12. So let's check at 17, that you can express 17 as a bunch of, so what does it really mean arithmetically? It means that you can express 17 as a some number of 3s plus some number of 7s, right? So 17 is 2 7s plus is 3. And 11 cannot be expressed this way, right? Because 11 cannot be expressed as a bunch of 3s summed up. And if I add a 7, it also doesn't help me because 11 minus 7 is 4. So I cannot express 4. So end of the proof. You cannot make 11 out of these stamps. But 12 you can, right? Because it's 4 3-cent stamps. So let's see. This is your theorem that any n over 12 can be expressed as some number of 3s plus some number of 7s. So is this predicate true about 12? Yes. I can just express it as a bunch of 3s and I don't take any 7s. 13 I can do as well. So I add 1 7 and I take away 2 3s. And look, when I add a 7 and take away 2 3s, so I added a 7 and I subtracted 6. So I added a 1. Therefore, I can repeat this operation. Add a 7, subtract 2 3s. And that's what I do here. I cannot continue because then there is no 3s to subtract from. So what do I do? Yes. So let's see. Actually, I will do a different move. But these 3 base cases suffice. Okay, now you don't know why they suffice because I don't show you the inductive step. I will do so in a second. But these 3 will turn out to suffice. So let's look at the following. So again, what were the 3? The 12 holds, 13, and 14. So that's my range. Remember, I needed to have a range of stuff about in the base case. And then the inductive proof is that anything within that range up to certain, however far I have gone so far, implies the next. And again, you have an extreme, I guess, example of not starting at 1. The base case starts at 12. All right. So here is this strong induction proof. If what I'm proving in the inductive step will be the following. The moment I have, my threshold is 14. If it is true that you can buy any amount of j between the base case start, which is 12, and k, right? So that's my variable range that starts from the inductive proof. It's this part. Started, in my case, at 12, ended at k. And I have to show that it holds at k plus 1. So that's my range from 12 to k. And based on that, I will argue that it holds at k plus 1. In other words, okay, sorry, I blanked that I had this thing. From P2, the predicate holds from P12 on all the way to pk, that it works now for pk plus 1. I have to show. And I have to show it for any case starting from 14, because for laziness or whatever reason, I only proved base cases up to 14. Okay, so here is the way this proof can be done. If k is 14, then I can subtract 2. If I move to the left by 2 steps, then I'm still above the threshold, the first base case. So therefore, this falls, the k minus 2 falls in the range of what I can assume. Therefore, this hypothesis of that j can be expressed as a bunch of 3s and 7s holds for j equal to k minus 2. So, but if k minus 2 is a bunch of 3s and 7s, if I add 3 to it, I will get what I need, which is k plus 1. I'm working backwards. I knew that I need k plus 1. I sort of guessed that, okay, if 3 cents less were expressible as a bunch of 3s and 7s, then of course this number, whatever this number is, can be expressed a bunch of 3s and 7s because you just add one more 3 to it. So all I need is that the predicate holds about 3 steps before this one. And that is true, right? Because so therefore you can buy the k plus 1 as expressed as a bunch of 3s and 7s because k minus 2 is expressible as a bunch of 3s and 7s, and now you just added one more 3 to it. That's why, yes, you have 0 3s, so you cannot subtract 3s anymore. After here, you will just be adding 3s. So look, take this P12, P3, 14, and add 3 to each one. Then this guy will imply P15, this guy will imply P16, this guy will imply P17. So you can write P15, P16, P16 as the next step in the inductive reasoning, and then add more 3 to each one. So it will go like a wave, and it will imply for every integer. The fact that in order to prove this, I needed that the predicate held 3 steps down basically meant that I had to do 3 by hand in here, because if the number of afterwards I'm building more and more, so good, but at the initial point I have to have 3 people here, or otherwise moving down by 3 is going to get me out of the range, right? So if I only had P12 and P13, and I try to prove this for here will be P14 on this side. If I subtract 3, I will get to P11, which doesn't exist, which is actually not true. That was my counterexample in the few slides back. This is I want to point out a few things more about this proof, okay? We proved this best case to 3 for 3 consecutive, and then we successfully argued this inductive step. In fact, we argued something simpler in a way. We only argued this step, this implication. It is a simplified form of this one, right? So what is the relation between them? Why didn't, we will turn out that we don't care. In order to prove this, all we need to know is this. We don't care about P is true about K minus 1. We don't care if it's true about PK. It's only we care about this. Is that a problem? Not really. It's still a strong induction. Because, look, what we have proven is that some A implies some B. What we were supposed to prove is that A, who is somewhere in here, and a bunch of other stuff implies B. Okay, that is a homework exercise for you. This hypothesis, this implication is proven if you prove this one. In other words, if you show that A implies B, then you also show that A and whatever implies B. Okay? So here I'm walking through the stuff that I already did. What if only I got super lazy and I only proved base cases like this? Then P14 would have a problem, right? So that's, I already said that. So here is Okay. I should end, but let's just leave off with this one. How it would generalize? You say you have to every n can be expressed as a bunch of 5s and a bunch of 7s, and it happens to be true after threshold 24. What is the base case here? So what do I need to prove? How many after 24 I need to prove that try to use the same thing, I guess, in your head. Yes, it's about, so people point to this one, right? And yes, indeed, it's this one. And the reason is that basically it's more convenient. There's less cases that you need to prove if you take the smaller one. So try to argue about P29 from these. So you don't care how it was done, you just use the induction. So 29 minus 5 is 24. So if you only prove these and you try to argue for 28, it wouldn't have worked, because 28, you know, if you try to take away 5 cents from it, you would be at 23, which this threshold is chosen for a reason. The statement is not true for 23. You cannot make 23 as a sum of 5s and 7s. All right. We'll do some more strong induction next time, and you'll be doing the stuff also in discussions. And I'll post next homework just so you can also start on this in case you're done with the previous one. And a quick announcement, I'll post it on Piazza. In order to reduce stress from tests, we were discussing with TAs and we decided to do the following. There will be a final exam for everyone. However, you will have an option, because I said that tests are it. I will stick by this. So if you want to, if you basically do well enough on these tests, you can just be graded on them. You will see how you're doing. And I will post some ranges where you can sort of see where your grade is gonna fall. If you can then decide to take the final or not, it's up to you. If you decide to take it, you cannot go back. Then your grade will be evaluated differently. There will be some weight on the final test, like let's say 30% or 35%. And the test in the quarter will be reduced in size, you know, proportionally. And then you're graded based on your test and the final, right? I think this is what it does is that because I'm first time teaching it in the 1 hour format, and we have this special situation of remote learning. So tests are now shorter. And I just think that's too much stress for some people. So if you are the kind of person that this is too, you know, that like maybe you will do badly because of too much stress, right? So now you have this final to you know, show. Perhaps it should be 40 on the final and 60 on the tests or something like that. Okay, but I'm not like reneging on anything I said before. If you choose to, test can be everything, and that's it. And then you don't have to worry about the final. Okay, so I hope you guys are okay with that idea. We sort of brainstormed with the TAs, and we couldn't think of a reason why anyone would feel like this is a bad thing. Okay, but hell we know. Okay, good. Next test, yes, the first test is October 30. Okay, let me, so please talk if you want to. So in other words, ask. I will stop recording.